Hello everybody. This pre-lecture will focus on calculating the enthalpy change for a reaction, delta H. So remember, the enthalpy change is really the heat flow. Is the reaction as it goes from reactants to products releasing heat, or is the reaction absorbing heat, exothermic versus endothermic? Now, if we want to define it a little bit further, we can say, it's a heat flow at constant pressure when only pressure volume work is done. Okay, that's technically what it is, but for our purposes, it's the heat flow in the reaction. So we're going to look at two different ways to calculate the enthalpy change, delta H. Okay, and remember, it's always a change in enthalpy. It's the difference in enthalpy, difference in the amount of, we'll use kind of heat and energy interchangeably. I mean, heat is a type of energy. It's the difference in energy between reactants and products. Okay, two ways to do this. Direct method, using standard enthalpies of formation, and we'll talk about what those are on the next slide. And then what's called the indirect method, or Hess's law. Okay, and they're different, but we both arrive at a delta H, and we'll see how these both work. Okay, so for the first method, the direct method, we need to know what the standard enthalpy of formation is. Okay, and the definition is it's the heat change that results, so this first bullet, when 1 mole, so make sure you note it's 1 mole of a compound is formed from its elements. Okay, 1 mole of a compound is formed from its elements. So remember, a compound is composed of 2 or more elements. It's one of the definitions that we covered way back when. 2 or more elements. So here's an example of a formation reaction. 1 mole of a compound, in this case liquid water, is formed from its elements, hydrogen gas and oxygen gas. Now we do have to write those as H2 and O2 because those are the stable forms of hydrogen gas and oxygen gas. They are diatomic. Now, one thing you'll notice in these formation reactions, quite often we end up with fractional coefficients. And that is because we need to end up with a coefficient of 1 in front of the compound, because it's the formation of 1 mole of that compound from its elements. It's okay to have fractional coefficients in this case because it's going to have to happen in a number of cases to end up with 1 mole of your product, your compound. So that is by definition what a formation reaction is. The enthalpy change can be measured for that. For this particular reaction, the formation of water, it's exothermic, negative, and it's 285.8 kilojoules per mole of water produced. Kilojoules per mole of water produced. All right. Now, these are all tabulated, which is really cool because you don't have to measure these. It's all been done. And one other thing to keep in mind, we will use this later when we do the calculation. Any element in its most stable form has a delta H of formation of 0. Any element. For example, hydrogen gas, that's its most stable form, diatomic gas. Okay, again, we're looking at, 25 degrees Celsius. Okay, same thing, oxygen gas. Okay, something like sodium metal that would be its most stable form, sodium as a solid. Mercury, another metal, really the only one that's a liquid at room temperature. Its most stable form at room temperature is a liquid. Okay, so an element in its most stable form has a delta H of formation value of 0. All right, so let's take a look at how we're going to do this. I guess the table comes up with these delta H formation values in a minute. Very simple equation. General equation, we're going reactants to products, of course. And to calculate the delta H for this particular reaction, so we're going to use Rxn for reaction. This superscript means standard state conditions. Okay. If you have a gas, the pressure of the gas is 1 atmosphere. If you have a solution, it's going to have a concentration of 1 molar. Typically, all these values that we're looking at, these delta H formation, they're measured at a temperature of 25 degrees Celsius. That doesn't have to be the case, but that's kind of the standard temperature at which these are measured. Okay, but gases at 1 atmosphere pressure, solutions are 1 molar. That's what we mean by standard state conditions. All right, so all we're going to do in this calculation is we're going to sum, that Greek letter sigma means take the sum, of the delta H formation values of the products, and we are going to subtract off, okay, so make sure you notice, subtract off the sum of the delta H formation values of the reactants. So just to reiterate this, sum together the delta H formations of the products, subtract off the delta H formation values of the reactants. But we sum the reactants together, sum the products together, subtract the two. Now, what about these N's? What do you think those mean? And you're probably right. It means moles. Or in a balanced equation, that would be equivalent to the coefficients. Okay? So you might not remember, but earlier we talked about, just one slide ago, formation reactions, the formation of 1 mole of compound. Well, if we're reacting 2 moles of compound, then the delta H is going to be double that. We've talked about that in class. Or if we're reacting 5 moles of compound, the delta H is going to be 5 times that. So we have to multiply by the coefficients in the balanced equation. That's all there is to it. Pretty darn simple calculation. So here's a table from your book. It's going to look really small on your screen. You don't have to see these values, but know that these are all tabulated. And you'll see up here at the top, these are standard enthalpies or heats of formation, delta H of formation, at 298 Kelvin, which is 25 degrees Celsius. To go between Celsius and Kelvin, we add 273 degrees. All right, so these are all tabulated for you. One other thing to note, elements in their standard state, bromine is a liquid at room temperature, delta H formation is 0. As a gas, it has a delta H formation value. Let's see if we can find some others. Fluorine, F2 diatomic, delta H formation is 0. But fluorine atoms, just fluorine atoms as a gas, does have a delta H formation value. It's only the element in its most stable state. All right, there's your table. So let's actually, I think, get to a problem, hopefully. All right. I apologize. I cut and pasted this from a problem that I had on an old exam. And for whatever reason, copying into OneNote, it didn't quite copy right, but for the most part. So use standard enthalpies of formation, okay, to calculate the enthalpy change for the reaction to make ethanol. There's your ethanol from carbon dioxide and water. All right, so there's your reaction. It's balanced. Make sure you double check that you have a balanced reaction because the coefficients are going to be important for our calculation. All right, and then if you're doing homework, you're going to have to look up these values. On an exam quiz, they'll probably be given either in the problem or on the back page of the exam. So these would be given. And there's your delta H formation values. Now, all we have to do then is use the equation. So our delta H for that reaction is going to be the sum of the moles times the delta H of formation of the products. And then we're going to subtract off the sum of the delta H of formation of the reactants. Again, we're going to multiply by the coefficients. All right, so let's just set this up. I think you'll like this calculation. You do have to be careful. Make sure you get everything in the right place. There's 1 mole of ethanol. So we're going to take 1 mole times the delta H. And you don't have to write it out in this much detail, but I'm going to do this the first time. So we're going to use the delta H formation of ethanol. Okay. We're going to sum, this means take the sum, of 3 moles times the delta H of formation value of oxygen. And I'm going to write it below here because I'm not going to be able to fit it all the way across. And we're going to subtract off the sum of the reactants. 2 moles of CO2 times the delta H of formation of CO2. Sum plus the other reactant, 3 moles of water, and that's the delta H formation of H2O. Now make sure you notice this is H2O gas, and that'll be important. The phase does matter. And you'll notice, because I'm a tricky guy, I gave you both H2O liquid, water, and H2O gas, water vapor. So you have both. Make sure you choose the right one. It's obvious in this case. All right, so let's start plugging in. Plug and chug. We like plug and chug, don't we? Okay, so 1 mole, delta H formation for ethanol, minus 276.98 kilojoules per mole, plus 3 moles. Now, you will notice that there is no delta H formation for O2, and I do this for a reason, because you should know what that is. Okay, it's not given. This is an exam question that I've used in the past. Delta H formation of O2 is not given. You need to know what it is. An element in its most stable form has what delta H formation? 0. Okay? And then we're going to subtract off the sum of 2 moles CO2 minus 393.5 kilojoules per mole. And then we have 3 moles of water vapor, so get the right value, minus 241.8 kilojoules per mole. All right, so let's do our calculation here. Oh, I'm running out of room. I'm getting to the next method. Let's squeeze this in here. So I'm going to go ahead and break this calculation into 2 steps. So the first one, we just have 1 mole times negative 276.98 plus 0. That's our sum. So we just have delta H is equal to negative 276.98 kilojoules. Our moles are going to cancel. And then we have 2 mole, then we're going to do this sum. Okay, so let's do that, minus this sum. So 2 moles times negative 393.5. Okay, and then we're going to add to that 3 moles times negative 241.8. And I get for this sum here, negative 1512.4 kilojoules. Again, moles will cancel. So one place that it's easy to make a mistake is with the sign here. You have to be careful. We're going to subtract off the sum of the reactants. Okay, so we're going to have a negative 276.98 minus a negative number. In effect, we're going to add this number here to that number. So let's see what we get. Looks like we're going to get a positive, so this would be endo, right? Heat absorbed, 1235.4 kilojoules. Okay? So that's the delta H for that reaction. Endothermic reaction, that reaction will have to absorb that amount of heat for that reaction to proceed. All right, calculating delta H by the direct method. I will give you this equation. Don't need to memorize it, but I think you will memorize it as you work these problems. Sum of delta H formation values of the products, subtract out the sum of the delta H formation values of the reactants to calculate the enthalpy change for that reaction, the difference between reactants and products. Okay, so that's one method, that's the direct method. Second method, indirect, named after Hess. So we're going to look at going from reactants to products in a series of steps versus one step. Okay? Now, it turns out that the delta H will be the same no matter which way we go. It's what is called a state function. And I'm going to switch back. I don't like a red pen. I only like that for highlighting. But it is a state function. Now let's change to green just for something different. So that doesn't matter which pathway we take. As long as we start in the same place and end in the same place, the delta, the difference, again, we're looking for the difference. So as long as we start with the same reactants and end with the same products, the difference in enthalpy will be the same. It doesn't matter the pathway that we get there. Okay? And this method, typically would be used if you can't synthesize a compound directly from its element, so you couldn't measure directly the delta H of formation value. We used to have so many tabulated now, we could get there probably, but this is just another method. So again, let's highlight what a state function is using an analogy. Think of yourself climbing up Humphreys Peak, if you've done that here in Flagstaff. The direct way, the way that you would normally go is you would start at Snowbowl and you would go up the Humphrey Summit Trail or whatever it's called, and that's about a 5-mile trail to the summit. But if you wanted to, you could start at Snowbowl and you could go down the Kachina Trail, which is about 6 miles, then you go up the Weatherford Trail, which is about 7, and you could cut over on the inner, looping around this inside of the inner basin. That's probably about another 3 to the saddle. So what am I at now? 13, 16, and then probably another mile from there to the summit, 17 miles. So you could do a 17-mile route up there versus 5. You're still starting in the same place. You're starting, say, at Snowbowl down here. And if you've never hiked up to Humphreys, you should do it. It's the highest peak in Arizona. Got to do it sometime. You're starting at Snowbowl. Here's our short pathway, the direct trail. This is wrong. I came up with 17. Okay. That's 5 miles to the top of Humphreys. All right. And then this is the other pathway. But we're starting in the same place. We're ending in the same place. Our delta is the same. Our difference in this case in elevation is the same. And that's what we're talking about in a state function. As long as we go from the same reactants to the same products, our difference, our delta in enthalpy will be the same. And that is the basis of Hess's law. So here's a figure from the textbook. It's just showing, we really want, which delta H we want? We want this delta H here. We want that difference between reactants and products. Okay, so that's the delta we want, but maybe we can't calculate that directly, but we're going to look at, okay, this reaction first, A plus B going to C, and then C coming to D, and again, these are just some generic reactants and products. Different pathway, but we're starting in the same place, we're ending in the same place, so our delta will be the same as going directly from reactants to products. Again, I think that makes sense. Again, it is a delta. So let's look at a quick, short example, and then we'll work one more, and that'll be the end of this pre-lecture. So here is the reaction we want to calculate the delta H for. All right. We have 2 known reactions up there. All right. So how are we going to do this? How can we arrange these two known equations to arrive at this equation? And by this equation is the equation that we want to find the delta H for. All right, so we just have to do some manipulation. I kind of look at these as they're a little bit of a puzzle, and this one's pretty simple. This first equation has what we want as a reactant. It has diamond as a reactant. That looks fine. That's what we want. So let's just rewrite the first equation. So let's start with number 1. And so rewrite that. Okay, so these are what are called allotropes. These are allotropes of carbon. Diamond's just made of carbon, so is graphite. All right. Now, since I didn't change anything here, my delta H stays the same. I just rewrote that reaction. All right. But this next one, I need graphite as a product. Here I have graphite as a reactant. So what do I do to that equation? Yeah, just flip it around. Flip our reactants and products. Now we're going to have CO2 gas going to graphite and O2. And we've talked about this before. If I turn the reaction around, what happens to your delta H? We change the sign. So it was negative 393.5. It will now be positive 393.5. Now, do these reactions add up to what we want? 1 mole of CO2 is a product. Remember, it's on the right-hand side of that equation. It's a product. Here we have 1 mole of CO2 as a reactant. We can cancel those out. 1 mole of O2 as a reactant in that equation. Second equation, 1 mole of O2 as a product. That'll cancel out. Now the moles have to, when you have to cancel equal number of moles from each side. And when we add these two equations together now, we end up with what we want. Only things left on the reactant side is diamond. Only thing on the product side is graphite. Since those two equations added up to what we want, we just add our two delta H's together. Okay, we added those two reactions together. We add our delta H's together. And I believe this comes out to negative 1.9 kilojoules. Exothermic. Okay, so there's the calculation. You have to manipulate the equations. This one was pretty easy. I'm going to do one more example that's a little bit more difficult. Exothermic reaction. We typically think of exothermic reactions as spontaneous. This one is indeed spontaneous. Okay, so diamond does spontaneously convert to graphite. Does that scare anybody? All the diamonds you have stashed away somewhere turning to just plain old graphite carbon from very valuable diamond to not so valuable graphite? Well, the good news is, and we'll do this next semester in Chem 152, the good news is that the reaction rate is really, really slow, and that's called kinetics, and we'll actually do reaction rates next semester. Really slow reaction. At room temperature, standard atmospheric pressure, you're looking on the order of about 1 million years. So I think you're okay with all your diamonds that you have stashed away somewhere. All right, last calculation. This did not print out as very well either when I copied it over from Word, but you get the idea. This is the one we want to find the delta H for. Can we take these two equations and arrange them somehow to add up to this? Again, it's kind of like a little puzzle. Just start with your first reactant and look for the equation that has that, and then you're going to have to do something to that equation most likely, maybe not, to get what you want. So I need 3 moles of Fe2O3. This equation has Fe2O3, but it only has 1 mole. I need 3. What do I do? I think it's pretty clear. We multiply by 3. So we're going to take this first equation and just multiply the whole equation by 3. So 3 times equation 1. That's what I'm trying to indicate there. So let's just do that. So we're going to be 3 Fe2O3. Now we have to multiply all the coefficients. 3 times 3 would be 9 CO. 3 times 2, 6 iron. And 3 times 3, 9 CO2. So we multiply that entire equation by 3. What happens to our delta H? We multiply it by 3. God, that's really difficult. Get the idea? That's why we talked about multiplying an equation by a factor, dividing by a factor, things like that, and how that impacts your delta H. Makes sense. We're now reacting 3 times as much. We're going to get 3 times as much heat released. All right, let's see what else I need. I need 1 mole of CO. Okay, so this is where it gets a little tricky. This equation has CO in it, and so does the top one. If I see a reactant or product and it's in more than one equation, I skip it. I'm going to skip CO for now because it's in both equations. It's going to be hard to figure out. Let's move on. Same thing for CO2. It's in both equations. I'm going to skip that for now. Okay, because it just makes it more difficult to try to figure out between 2 equations what I really need. So I'm going to go all the way over to my last product. And I need 2 moles of Fe3O4 as a product. Well, let's look at equation 2. That has 1 mole of Fe3O4 as a reactant. So I need to flip that around to get it to the product side. And what else do I need to do? Multiply by 2. So I'm going to take the second equation and multiply it by 2. Right, this second equation up here, but I also have to flip it around. So I'm going to start with my products, and then 2 times 3 would be 6 iron. 2 times 4 would be 8 CO2. 2 times 4 would be 8 CO. And 2 times 1 would be 2 Fe3O4. So I did get my 2 moles of Fe3O4 as a product. Now, my delta H, I multiplied by 2. But I also turned it around, so it's going to change the sign from negative to positive in this case. All right, and there we go. So, does this work out? Do I end up with the equation that I want? Well, let's see. We can start canceling things. We have 6 moles of iron on the product side, 6 moles of iron on the reactant side. That goes away. Now the CO2 and CO is a little bit trickier because I have 9 moles of CO on the reactant side. I only have 8 on the product side. So I can cancel 8 here. I can cancel 8 here, leaving me 1 mole of CO on the reactant side. Same thing here. Cancel 8 CO2 on the reactant side. I can cancel 8 from the product side, leaving 1 mole of CO2. All right, does that add up? 3 moles of Fe2O3, 1 mole of CO, going to 1 mole of CO2, and 2 moles of Fe3O4. Is that what we want? Yep, sure is. So we manipulated those 2 equations. You can see this one was a little bit more complex than the previous example. All right. Sometimes you'll have 3 or 4 equations that you have to put together, not just 2. So it can get a little bit more difficult than this. All right, now we just have to add these together to get the delta H of this reaction. So 3 times a negative 28. Okay, that's a negative 84. 2 times 12.5 is going to be 25, so we're going to add 25 to that. And we should get a negative 59 kilojoules for this reaction. Okay? Exothermic. There you go. 2 ways to calculate delta H for a reaction. Direct method using delta H formation values. Hess's law, kind of a puzzle. We're going to take known reactions with known delta H's. We're going to manipulate those equations to try to add up to the equation that we would like to calculate the delta H for. All right. Hope this helps you in calculating delta H, and I will see you soon. Take care.